Chapter 9, Section 5. In Chapter 4, we learned how to find critical points for single variable functions. We also took an in-depth look at how we could optimize functions by finding local maxes, local mins, global maxes, global mins. In other words, we use specific methods to find the largest or smallest value of a function. This section elaborates on the concepts we learned by applying them to functions that have two variables. So we're going to be looking for critical points, maximums, and minimums. General guidelines. For a function f, defined on some domain of real numbers, we say that f has a local maximum at p0 if the y values for that function are greater than all other y values for all points near that point. We have a local minimum at p0 if the y values of the function are less than the other y values for that function at the point p near p0. We have a global maximum if at the point p0 we have y values greater than other y values for all points defined in our function. And we have a global minimum at p0 if the y values are less than all other y values for all given values. These guidelines will seem clearer as we learn more about how two variable local global max and mins functions work. Let's start with a table. Tables are the easiest to find values for. So given the table of values for a function f of xy, estimate the location and value of any global max or min for x from 0 to 1 and y from 0 to 20. Now, because the table gives us the actual function values in the middle, we are literally going to look for the largest value and the smallest value to obtain our global max and our global min. Doing a quick scan of all the values in the middle, we find that 49 is going to be the largest of all the possible values. And if you look, 49 is going to happen when x is 0.6 and when y is 15. So the global maximum will be 49 at the point f of 0.6, 15. Similarly, for the global minimum, we're going to look for the smallest value. A quick scan through all the values will reveal that the smallest functional value is going to be 30. And 30 is going to happen when x is 0 and when y is 10. So the global minimum is 30 at the point f of 0, 10. Like I said, to the easiest because we're going to literally just find the largest and smallest value. But we also want to be able to do this analytically with functions. So how do we do this? So if a function f of xy has a local max or min at a point x sub 0, y sub 0, not on the boundary, meaning it's not at a or b when x is between a or b, then either the partial derivative equals 0 for both the partial with respect to x and y, or one partial derivative is undefined at that point. So that means if you have something like 1 over x, at x equals 0, it's undefined because you can't divide by 0. So either you're going to have something that's undefined or both first partial derivatives will equal 0. So points where each of the partial derivatives is either 0 or undefined are called critical points. Remember, just because a critical point exists somewhere doesn't necessarily mean that it's a local max or a min at that point. After we learn how to do these computationally, we'll also learn how to classify them as local maxes, local mins, or neither. So let's start with an example. We want to be able to first find critical points. That's going to be our first basic thing that we need to do in order to classify them. So let's say we have the function 2x squared minus 4x plus 2y squared minus 12y minus 3. In order to start talking about critical points, we're going to need to calculate the first partial with respect to x and the first partial with respect to y. So let's start with the partial with respect to x. Remember, the partial with respect to x means that y is a constant. So we come up, the first term, 2x squared, has our variable of x in it. The derivative of 2x squared is 4x, this first term. The second term, minus 4x, the derivative of minus 4x is minus 4. The derivative of 2y squared is 0 because this term is a constant. 12y is also a constant, so the derivative is 0. 3 is a constant, so the derivative is 0. So our first partial with respect to x is 4x minus 4. We set that equal to 0. We also want to find the first partial with respect to y. So again, that means that y is our variable and x is a constant. So the first term is constant, the derivative is 0. Second term is constant, derivative is 0. Third term, 2y squared, the derivative is 4y. The derivative of minus 12y is minus 12, and the derivative of 3 is 0. So our first partial with respect to y is 4y minus 12. We set each of our first partials equal to 0 to see how easy it is to solve. In this particular case, it's nice because both of our first partials have reduced into linear forms, which are quite easy to solve. So if 4x minus 4 equals 0, that tells me that x has to equal 1. For our second partial, if we have 4y minus 12 equals 0, add 12 to the right, divide by 4, and I get y equals 3. So here, we have found that our function f has one critical point at the point 1, 3. Now, not all of them are this easy to solve, and we'll definitely look at some that are a little more complicated, but it is nice when they both reduce down to linear functions. So, how do we know if this critical point is a local max, a local min, or neither? Okay, how do we classify these? So what we're going to do here is we're going to use a second derivative test. We used a second derivative test to classify critical points when we had single variable calculus, and we'll use a second derivative test here. Only the test here is a little bit different. So, suppose that x sub 0, y sub 0 is a critical point, so we've solved for some critical point, and we know that the first partial with respect to x and the first partial with respect to y equals 0. That's how we found it. So now we're going to define this term d. So d is going to be the second partial derivative with respect to x at our critical point times the second partial derivative with respect to y at our critical point minus the mixed partial second derivative squared. So we're going to have to calculate these second derivatives when we try to classify this, and then we'll be plugging our critical point into it. Once we have a value for d, which will just be a number, we have several cases. D could be positive, D could be negative, or D could be 0. If D is 0, the test is inconclusive and we can't figure it out with the methods that we have. If D is less than 0, then F has neither a local max or a local min. So those are the two cases where we can't get too much information. However, if D is positive, a positive number, then we want to look at the second partial derivative with respect to x term. If that's also positive, then f has a local max at our critical point. If the second partial with respect to x is negative, then f has a local max at our critical point. And so we'll use this test to figure out local maxes, local mins, neithers, or inconclusives. There's a handout in the folder at the top of Chapter 9 which has this test printed out for you, so if you'd like to print out a copy while you work, that may be helpful for you. So let's go back to our example. This is the example we looked at before. We found our first partials. From there we solved for our critical points. We had a critical point at 1, 3, and now we want to find out, is it a local max, a local min, or neither? So again, we're going to use the second derivative test. In order to do that, we're going to need the second partials with respect to x, y, and the mixed partial. So let's remember what our first partials looked like, 4x minus 4 and 4y minus 12. Okay, so from here, our first partial with respect to x was 4x minus 4, which means our second partial with respect to x, we go back to our first partial and take the derivative with respect to x. The derivative of 4x is 4. The derivative of 4 is 0. For the first partial with respect to y, we had 4y minus 12. So then if we take the second partial with respect to y, the derivative of 4y is 4. The derivative of 12 is 0. So our second partial with respect to y is also 4. Then we need to find the mixed partial. So if we take f sub x and then we let y be our variable, we can see that 4x and 4 are both constants. So if we take the derivative of either term with respect to y, we get 0. Similarly, if we start with the partial with respect to y and look at that function, and then let x be our variable to get f sub y x, both these terms are constant, so the derivative is 0. Remember that the mixed partial derivatives will be the same. So now that we have our 4 second derivatives here, we go back to D and we say, okay, what are our values at the critical point? Well, here it's not so interesting because we can't plug anything for x or y since we only have constants, but we can still do the analysis. So D, which is the value we're looking for, is the second partial derivative with respect to x, which was 4, times the second partial derivative with respect to y, which is 4, so 4 times 4, minus, then our mixed partial derivative was 0 squared. So that gives us 16. So by definition, our critical point is going to be a local minimum, because D is positive, so that means we're going to have a local max or a local min, and then our second partial with respect to x was also positive. That tells us that f has a local minimum at our critical point. So here, let's do another example, but now one that's a little bit harder to solve for our critical points. So suppose we want to find the critical points for the function x squared minus 2xy plus 3y squared minus 8y. So the first thing we need to do is find our first partial derivatives with respect to x and y. So when we do it with respect to x, that means y is a constant. So for our first term, the derivative of x squared is 2x. For our second term, 2 and y are constants that are multiplying. So we have a constant times x. So the derivative of a constant times x is just that constant. The third and fourth terms don't have any x's in them. So they're just constants and they go away when you take the derivative. So the first derivative, partial derivative with respect to x, is 2x minus 2y. For the first partial with respect to y, x is now going to be a constant and y is going to be the variable. So x squared is going to be a constant. The derivative of a constant is 0. For the second term, the minus 2x is a constant times y. If you have a constant times y, the derivative is just that constant, that negative 2x. The derivative of 3y squared is now going to be 6y, and the derivative of minus 8y is minus 8. So we can see here that our partial derivatives each have an x and a y. So that makes it a little more complicated when we set it equal to 0. There's a few different ways we can solve for values of two variables. We'll discuss how to solve this problem by adding two equations and solving for our variables. We can combine the equations this way because they share the same point. And we'll also talk about how to do this with direct substitution. So we're actually going to solve this two ways and we'll get the same answer. So whichever you're more comfortable with, you can use. So let's try our first method. So we take each of our partial derivatives that we've solved for and set them equal to 0. So 2x minus 2y equals 0 is our first equation, and minus 2x plus 6y minus 8 equals 0, our second equation. If we solve our first equation for x, we bring the 2y term over. So we have 2x equals 2y, divide by 2, and we get x equals y. If you can solve for one variable, you can then plug that into the second equation. So if x equals y, that means that for all the y values, we can plug in an x. So minus 2x plus 6x, because x equals y, so we're plugging in an x, minus 8 equals 0. Now we can combine the x terms, 6x minus 2x, so we have 4x minus 8 equals 0. And if we solve for x here, we get x equals 2. Well, since x equals y, if x equals 2, y equals 2. So we get a critical point of 2, 2. So that's the first method of solving, where we can solve one equation for one variable, and then substitute that into the second equation. The second way to solve, to get the same critical point, is to add our equations together. So the way we do that is we line up our equations, we put one on the top and one on the bottom, and we add down. Since they equal the same thing, we can do this, and notice that the two x terms are going to cancel. Okay, so here, 2x minus 2y, that was our first partial, and we're going to add that to the second equation, which is minus 2x plus 6y minus 8. Adding down 2x plus negative 2x cancels the x term out. Then we have minus 2y plus 6y is 4y, 0 plus negative 8 is minus 8. So we have 4y minus 8. So we've canceled the 2x from both sides. Both of them equal 0. So we end up with 4y minus 8 equals 0. Solving for y, we get y equals 2. So now that we know that y equals 2, we can plug it into either one of the equations to solve for x. So if we plug it into the 2x minus 2y equals 0 equation, we get 2x minus 4 equals 0, or x equals 2. So now again, we found that our critical point is the point 2, 2. Either method will work to solve for the critical point. Whichever one you're more comfortable with you can use, and there are certainly other ways to do this, but these are the two most typical. Now that we have our critical point, we want to know, is it a max? Is it a min? Is it neither? So again, we have to go back to the second derivative test. So remember, our first partial derivative with respect to x was 2x minus 2y, which means our second partial with respect to x will take the derivative of the first derivative with respect to x. The derivative of 2x is 2, and the second term is just a constant. There's no x's there, so the derivative is 0. So f sub xx equals 2. If we take our first partial with respect to x, and then take the derivative with respect to y, the 2x term is a constant, so it's going to go away to 0, and the derivative of minus 2y with respect to y is minus 2. So the first mixed partial, f sub xy, is minus 2. Now going on to our first partial with respect to y, we had minus 2x plus 6y minus 8. So if we then take the second partial with respect to y, the first term doesn't have any y's, so it goes to 0. The derivative of 6y with respect to y is 6, and the derivative of minus 8 is 0. And again, our mixed partials should be the same, but we'll just double check. So now if we take our first partial with respect to y, and then we take the derivative with respect to x, the derivative of minus 2x is minus 2, and then the other two terms are constants, so they go away. So our mixed partial is minus 2 in both cases. Now that we have all four second derivatives, we can solve for d. Using our equation, f sub xx at our critical point, 2, 2, is just a constant of 2. So we plug in that. F sub yy we found to be 6, so we have 2 times 6 minus the mixed partial, which is negative 2 squared. So 2 times 6 is 12, minus 4 is going to give us 8. So now, by definition, our critical point, 2, 2, is a local minimum. Because again, if d is positive, which it is here, 8, and the second derivative with respect to x is also positive, which it is here, it's positive 2, then f has a local minimum at our critical point. So if you want to see some more examples, you can look at the folder at the top of Chapter 9, and there's several more examples of using the second derivative test and calculating these partial derivatives.